Miss Nan Jiang. So
Yes.
yes, and he is continuing his PhD at the Department of Physics, University Virginia, USA at presently, under supervision of Professor Kent Yagi, and he did his graduation from Department of Physics, Jilin University, China. So it is pleasure for us to have talk from her, and his title of talk is Improve Analytic Modeling of Neutron Star Interior. So
Bhuya, she, not he.
okay, see, okay, okay, see. So today we have a person, we have some notes on that, because after the talk we have question session. So in between we do not have any question session.
Okay. Okay.
Okay, thank you. Now you can start the talk.
Okay. Thank you very much for having me to give this talk on my recent works, and it's a total pleasure for me to give this talk. My topic today is the improved analytic modeling of neutron star interiors. First, I will give a very brief introduction of the Tolman VII solution and how we improve this Tolman VII modeling. And then I will compare the differences between the original one and and our improved version of this Tolman VII solution. And then I will give this conclusion and future directions. First, people need to construct neutron star solutions to relate the neutron star observables to the internal structures, like the nuclear, like the inner nuclear structures. And there are some analytic neutron star solutions, which are like the constant density solution and the Bookdown solution. And most importantly, the Tolman VII solution. The Tolman VII solution is actually extensively studied, and it is proven to be stable for a large range of compactness, and its geometric structures are studied. And you can see the relevant studies in the following references. First, what is the Tolman VII solution? Tolman VII solution describes the static and spherically symmetric neutron stars made of perfect fluid. And you can see that from the metric in equation 1 and the energy density metric for the equation 2. And here, instead of instead of an equation of state, Tolman just specified what is E minus lambda is, and here it is and here he gives this E to the minus lambda to be a quartic function of R, which gives the energy density function to be a quadratic function in R and radius. And here you can see that rho c can be replaced by mass and radius. So this model is a two parameter model parameterized by either mass and radius or the central energy density and radius. And then after applying the boundary conditions, like for the E nu and the pressure, then Tolman can solve for the nu and p to be expressions like equation 6 and 7. And in equation 6 in phi in the phi Tolman expression, there is also an integration constant, and I didn't wrote it here. It's just like there are two integration constants in equation 6, and this is the Tolman VII solution. And And this is how Tolman VII solution behaves for this example star, which is AP4 equation of state and 1.4 solar mass. And you can see that for the rho profile, the original Tolman solution in terms of radius and central density is slightly better than one in radius and mass for the region near the center. And for the pressure profile, the mass and radius parameterization is better than the rho C and R. So I mean, like, you can see that in order to give a very good description of the neutron star, we may need three parameters, which is rho C, R, and big M. So like, how do we combine? Like, I mean, like, how do we make rho C, R, and M like all enter this expression? And here we propose a revised model with three free parameters, M, R, and rho C, by introducing an additional term to equation 3, which is this term, the one quartic in R. And here we can just find this mass profile to be formed like this according to Einstein's equation. So like here, I have to say that in our paper, we adopt 11 realistic equation of states, which has soft, intermediate, or stiff stiffness. So how do we get this alpha so like this alpha is very messy because previously we obtained this alpha by fitting this expression, by fitting this equation 8 with the numerical profiles. So like, I think in order to make this model useful, we have to find an analytic expression for alpha. So our first guess is inspired by equation 9, which is this one. If you set the R equals radius, and this M is just the mass of the star, and you can get an equation for alpha. But this one is very bad because the values produced by this expression has very big deviations from the actual alpha. So we just add a higher order terms, like this square terms, and also we make the power of the compactness to be something in our choosing. So we found a particular relationship, which is this. If we set the power of the compactness to be 0.903, then all the alphas for all the equation of states and masses can have this nearly equation of state independent relation, which is like this, and the Frag error can be less than 10%. So we decide to use this universal expression for alpha to be the expression for alpha. And we plotted the same thing for our improved model, which is these graphs. And you can see that the red ones are our improved model, and it has a very good convergence with the numerical profiles compared to the original Tolman case. So next we have to find the nu and pressure profile. So, but however, in this case, the Einstein's equation cannot be solved analytically. And we also tried many other methods like the perturbation series and resummation, but they all don't have a very satisfying outcomes. So instead of proposing some new expressions, we just revise the original Tolman with modified boundary conditions. So like here, you can see that the equation 12 is the same as the original Tolman solution. But here is this equation 3, this pressure, instead of the e to the minus lambda Tolman came up with, we use our improved e to the minus lambda. And we use this to find the new integration constant as in equation 14. We still use the same boundary conditions, but with different pressure and different e to the nu. And then we will have different C1 and C2. And then as for the pressure expression, we cannot use the one from equation 13. This one is only good for determining the integration constant. But however, for the whole profile, this is not a physical solution because it is not it is not a solution to the Einstein's equation. So like here we just modify this expression and make it to be one which satisfies the Einstein equation, and also it can vanish to zero at surface, and that's how equation 15 came about. And you can see that this E lambda is the original Tolman lambda, and we also have this constant to shift this profile to zero at surface. And then that's our result. And you can see that for the gravitational potential nu, it has a very good accuracy describing the numerical solutions. And also for pressure, maybe it is not maybe it is not perfect for the whole profile, but for the area near the center, our model has a very clear and obvious advantage over the previous original Tolman case. But we just discussed one particular example, and this is not enough. So here we introduce a measure for the error, which is called relative root mean square error, to see like how our models behave over a range of methods for different equational states. And the definition is given in equation 16. This RMSE just shows how concentrated the data is around the numerical results, and the smaller it is, the better or the more accurate the model is. So for the density case, for all the 11 equational states pictured here, and you can see that the red ones are the soft equational states, the green ones are intermediate, and the blue ones are just stiff equational states. And you can see that we have a pretty good improvement for nearly all equational states, especially for the soft ones, which is a more favorable equational states by the discovery of the LIGO. So like and also for the mass profile, we also have a very great improvement over the original Tolman case, and also this original Tolman is parameterized by mass and radius. So like for nu, we also have this good behavior. And you can notice that there is one equational state which has a pretty bad result, which is this blue state funds. How do I say? Yeah. So like actually this is Shen. This equation state corresponds to Shen, and it is it is nearly ruled out by LIGO's discovery. So I think it is fine. And also for pressure, actually for pressure, you can see that for solar mass, for the neutron stars with very small masses, the original Tolman is actually better than our model. However, for larger masses, our model can outbehave the original Tolman. So in conclusion, we just proposed a 3-parameter model, which further raises the Tolman VII solution's accuracy in modeling numerical solutions with different equation states. And here you can see that our relative RMSE or the improved model has a general better accuracy than the original Tolman model. As for the future directions, I think one is we can find more approximate solutions to the Einstein's equations, or we can go further and find a better density profile ansatz. And also one can just infer the central density in terms of mass and radius using our expressions. And also this result is the first step for the construction of neutron stars interior solutions with slow rotation and tidal deformation. And there are other possibilities which are like improve other analytic models, such as the book dot solution. Yeah, and I think that's it. And thank you for your patience and listening to my talk. Thank you.
Okay.
Okay, thank you very much, Jiang.
Yeah.
Now it's the time for question.
Okay.
So please.
Okay, Jiang, I have a question.
Okay.
So you have used soft equation of state intermediate as well as for stiffer equation of state. So in one case you have used SLY4. Okay. So in original Tolman case, the SLY, the maximum mass is 2.05 solar mass, right?
Yes. Yes. I think all those equational states support like neutron stars with mass like greater than 2.1 solar mass.
Okay. So in your case, you have improved original Tolman equation, right? So the mass, mass is how much in case of SLY4?
Can you repeat that? I didn't listen to that very clearly.
So what is the maximum mass corresponding to the SLY4 for improved Tolman modeling?
And also radius.
Hello? Can you go to the can you go to the slide number 20?
Okay, yes.
Yeah. So here in the table, you have shown that the original Tolman gives the maximum mass up to 10%, that RMS radius, RMS SE, root mean square deviation. So after you have improved the Tolman, this percentage error is reduced up to 4%, right? This means your model is better than the original Tolman.
Yeah, I think it is. Yeah, I think it is just more accurate in modeling the numerical solutions.
Yeah. So my question is that what is the maximum mass corresponding to the SL by 4 in case of improved Tolman? Yeah.
You mean the mass radius?
Yes.
Actually I haven't plotted that. I can give you the plot if like.
Okay.
Yeah.
So,
sorry about that.
Okay. So how do you fit the alpha value? That alpha value.
Oh, the alpha values.
Yeah. You have shown some universal relation. Yeah. Universal relation versus that alpha versus the compactness versus the central density multiply the radius square, right?
Yeah.
So how do you choose alpha value from here?
You mean like how do I choose alpha values, right?
Yeah. So because you have shown somewhere some expression where the alpha you have mentioned. So for example, in case of canonical neutron star, what is the value of alpha? Yeah. Here.
Yeah. So like here
in equation 11. Yeah. In equation 11, what is the value of alpha in case of canonical neutron star?
I think this A0, A1, and A2 are just like fitting coefficients. I got them just from doing the fit. It doesn't have an analytic expression for A0, A1, and A2.
Okay, this is the coefficient value. So this coefficient value is less than 1, right? A0, A1, A2.
Oh, okay. Yeah. Yeah, it's just the fitting parameters. So like it is obtained like numerically. Like you have to do the actual fitting.
Okay, so for example, in the value of A0 is less than 1, right? In equation 11.
I don't know the. Yeah, I don't know the actual value for A0, and it's given in the paper. Like I have given the values for A0, A1, and A2.
Okay. Because this relation, just like when you are fitting the Euler relation, similar expression will come.
Oh yeah.
A0, A1, and A2 square.
Oh yeah. But it's but it's not that. Yeah.
Okay.
Thank you for your question.
I have one question.
Okay.
Hello. So you have shown that you have fitted the central density in terms of some coefficient alpha and zeta.
Can you repeat that? Yeah.
So you have shown in some expression you have fitted improved the central density expression with some empirical formulas, something like that. Rho C.
Yeah.
So what is the physics behind this? So what is the actually what is the physical point of view to fitting the central density in such a way?
Yeah. So actually, this Rho C
hello, I can give this answer. Suraj, I can give this answer. So whenever you are talking about universal relation, universal relation generally they are plotting x and y. Okay, so both the values should be in the both places. So if you see the equation 11, c divided by rho c into r square. Okay. So
no.
Completely dimensionless quantity.
No. Bharat, you just listen. So in one of her expression, she has shown that central density is a dependency on alpha parameter, and alpha means that is mass. I think because alpha expression contain the mass. That means the central density contain the mass and the radius.
Yeah.
So what is?
I just think that. Yeah. I mean,
the physics behind this. Why one should thinks that the central density should be a function of mass and radius?
oh, I think maybe you can think of it in a different way. I think it's more like the mass and radius is a, I mean, it's like a function of rho c, like the
Of
mass.
central density. Yes.
Yeah, and I think that's how you think about it. And you can maybe infer rho c from mass and radius.
Okay, okay. You just reverse these things. Means the central density is also function of mass and radius.
Yeah.
Because generally, if in the TOV equation we just first put central density, then we get mass and the radius.
Yes, yes, yes. That's
Then you reverse. Then you here reverse it. The mass we put the function central density as a function of mass and the radius.
oh yes, I think maybe you can do that.
Okay.
In this case.
And another in your last slide, somewhere you have shown that in case of here you have in just previous one.
Mm-hmm.
Somewhere you have shown that in the lighter mass case, your error bar is less than in
Go
case
to
of
the
maximum.
20 number slide. Go to the 20 number slide. He's asking
Oh,
20 number.
oh,
Yeah.
okay, okay.
No, not the previous one. Another just
19.
before
This
19,
one?
19,
Yes,
19.
yeah.
Okay.
No, you have somewhere you have shown that in case of lower mass, the error bar is less, but in case of higher mass, the error bar is high. Because
no, I think for higher masses, the improved Tolman case is better than the original Tolman. But for the smaller, yeah, our model is slightly worse than original Tolman.
Oh, your improved model is not working well for the lower mass, but it's working well for higher mass.
Yeah, I think it is better in the higher mass region.
So why it is so? Why it is so?
Actually, I don't know the answer to this. I can just say that for the original Tolman, it is just very good in the lower mass.
Oh, yeah, I can hear you.
Yeah.
Hello?
Hi. Yeah.
I cannot hear you actually.
Oh, yeah. I just think it's because the original Tolman has a very good behavior in the lower mass regime, but I'm not very sure like, why it is very good in the lower mass region and very bad in the higher mass region. Actually, I don't know that story. Yeah.
So lower mass means which lower mass? You are saying 1.4 solar mass or 1.2 solar mass? What is the minimum limit you are talking about for lower mass?
Lower mass is like nearly one solar mass, like it's around one solar mass for the low mass region.
So the improved one is better starting from 1.4 solar mass to higher regions, right?
Yes, I think for the smaller mass, our model is not that like better than the original one. Like for the small mass region.
Okay.
Because here in the upper panel and the lower panel, it is clearly visible that the relative error what the original Tolman and improved Tolman with universal parameter alpha is get improved, except that blue color, some parameter that one.
Yeah. I mean, like except the state equation-of-states. Like for
Yes.
the Shen case, it is not very perfect. Like.
Okay.
So the disadvantage in your model is only that your model is not working for lower mass region, but it is very well working on at higher mass region, right?
Yeah, I think so. And also for the soft equational states, I think it is pretty useful for studying the soft equational states.
Okay.
It has, yeah, it
Okay.
has, yeah, yeah.
So in case of stiffer, your model little bit deviated for original one.
The relative error is little higher in case of mass around 1.1 or something like that.
One minute. A soft equation of state means it can produce the maximum mass around 2 or less than 2.
I think it's like 2.1 plus or minus some 0.
Okay. That recent observations. It can reproduce the recent observation, I think.
Yeah.
The soft equation of state can also reproduce the recent observation of maximum mass of neutron star.
Huh?
Whatever you are talking about the soft equation of state, this soft equation of state can reproduce the maximum recent observation of maximum mass of neutron star.
I think they can all support the maximum, like the 2.1 solar mass.
2.1. Okay.
Okay, yeah. Subrat, let's give chance to other. Okay. Okay, is there any more questions from other?
Yeah.
Yes.
Okay.
Actually, I could not understand the error. What is error corresponds to?
So here they have put given the root mean square error, that is RMS relative error for different parameter plotted in the upper panel. This is for original Tolman equation, and the lower is for Tolman equation with universal parameter alpha.
No, but how do you calculate this error? I'm not able to get it because you have two different models.
I also don't understand.
That is a little complicated because she don't know actually how they distinguish these two models, and because they both are from the error can only justify.
Yeah. Just go to the 16x. Jiang, can you explain this equation number 16?
Oh, what?
Can you explain this equation 16 again?
Okay.
Equation 16.
That's page 16, right?
Not slide number 16. Equation 16.
Okay. Yeah. Okay.
Yeah, this one. Root mean square.
Yeah.
You can explain a little bit more.
So like, do you want me to explain how do I calculate the RMSE?
Yes.
Yeah. Okay. So like you can see that like here in the numerator we have this integral over the whole radius of this one neutron star. And here I have already have the Y model, which is the analytic expression for the mass and the mass rho, nu, and p. And for this Y numerical, we have already produced that, like the it is just the numerical results of the solutions.
So by error you mean exact result which is you obtain numerically with respect to the analytical result which you are obtaining from the analytical solutions actually.
Yes.
Different model have two different.
Okay, so basically your analytical results are not good at a lower mass. Your analytical results.
You repeat again.
Your analytical result. See, the most accurate result you have is a numerical one.
The numerical ones.
Numerical ones are the accurate ones, right?
Oh yeah, like it is solved numerically by plugging the all the realistic equational states.
Exactly. That means at the lower mass, your analytical result is not matching with the numerical ones at the lower mass.
Yes, I
For
think
lower
so.
mass, you have large errors.
Yeah. I think in the case of pressure, it is not better than the original Tolman.
Okay. So just
Yeah.
now I understood. Like error means the difference between the numerical result and the analytical results.
Yeah.
That is
Yes.
what by error.
Yeah.
Okay.
Yeah.
Okay.
Other
Okay. Thank you.
model two difference results come by that.
Can you repeat that? I didn't hear it very
Okay.
clear.
Is there any more questions?
Yeah.
Is if not, thanks the speaker.
Can I say one more thing before I go?
Yeah. Thank you very much.
No. There's one more thing I want to say before I end this. So like
Yes. Go ahead.
I mean, if you look at my paper and there is a table of formulas, and there is a typo actually in the expression for C1 and C2, and I will modify that. Very soon. Like, yeah. So like, I just want you to know that there is a typo, and I will fix that, like by next week. If you want to refer to my original paper, yeah.
Okay. Thank you.
Okay.
Thank you.
Okay.
Thank you, Jen. Okay.
Sorry about that.
Okay,
Yeah.
good talk.
Hello. Can you just give any link to your papers?
It's in.
Very nice work. First of all.
It's on archive. I can send you. Yeah. Like this is the archive number, and you can search for it. It
Okay.
is very detailed. Yeah.
Okay. Thank
So-
you very much.
Anyway, tomorrow I will upload this talk on YouTube, so you can watch again and see this archive link, all these things. Okay then. Thank you, Jen.
Thank you
Bye.
very much. Yeah. Bye.
Okay. Thank